Hey everyone, in this video lecture we are going to be covering the topic of non-renewable energy. So the chart here is just indicating which topics from the CED for this course that will be covered in the video. So this slide is just to recap what we've already gone over in class, that our non-renewables can be grouped into two categories. There are the fossil fuels, which consist of oil, coal, and natural gas, as well as nuclear, which comes from the radioactive fuels such as uranium. So if we go through each of these non-renewables, we're going to look at how they form, how they're extracted, where they're found, and how they're used for electricity. So hopefully from class, you've kind of gotten a sense that for all of our energy sources, there's kind of a pattern for how we use them to generate electricity. So the majority of these energy sources that we're going to talk about today help us create electricity. And so the way it works is we take the fuel, so whether it's one of the fossil fuels, whether it's uranium, and we burn it. Well, uranium we don't actually burn, but we'll talk about that in a minute. But typically there's heat. So we need heat. That heat is then used to heat up water to create steam. The steam spins a turbine. That turbine powers a generator, which then produces the electricity that reaches our grid. So you want to remember that kind of chain of events for electricity generation because this applies for all of our non-renewable sources. Nuclear is slightly different, but for the other three fossil fuels, they are burned to produce that heat. In terms of electricity generation here in the United States, coal is our number one source for generating our electricity. So we're going to go through and talk about the fossil fuels first and thinking about how these form underground. So coal forms slightly differently than the other two fossil fuels. Overall, the process is similar, but what makes coal unique is that it comes from plants and animals that were decomposing from swampy forests millions and millions of years ago. So in these swampy forests, you had plants, you had animals that died, their organic matter started to break down and decompose, and what happened is layers of rock started to accumulate on top of the decomposing organic matter, and that vegetation begins to turn into what we call peat, which is like partially decomposed organic matter. And over millions and millions of years, enough heat and pressure from the layers of rock above lead to that organic matter forming into a hydrocarbon, which is just long chains of carbon and hydrogen into what we now know as coal. And there are different types of coal, and typically it's found deep underground. There are pockets of coal that are a little bit closer to the surface, and we'll talk about how that coal then gets extracted and used today. So the other two fossil fuels, oil and natural gas, similar process. However, coal was specifically coming from organic matter that was in swampy forests. For oil and natural gas, the organic matter is mostly algae and phytoplankton that was in the ocean. And so when these tiny ocean plants died, they started decomposing. Similarly to coal, layers of sand, silt, and rock build up on top of the organic matter that's decomposing. And over enough time, the heat and pressure from those layers above create those hydrocarbons. And within the layers of rock, what happens is there's typically sitting on top of that decayed organic matter, there's this layer of impermeable rock, which means liquids, gases can't pass through it. It's like a cap, if you will. That traps the oil and gas against that rock, that impermeable rock. And the oil and gas do have different densities, so they'll separate into layers where natural gas will actually rise up and sit on top of oil. And typically below the oil, you'd find pockets of water. So that oil and natural gas do separate from one another. But oil and natural gas form in a similar manner to coal. It's just really that starting organic material is what's different. So now that we understand how they form, we want to be able to extract these fossil fuels from the ground. And so typically what is used are mines or wells. So for coal, those pockets of organic matter are typically closer to the surface. They can still be really deep, but depending on how far down it is, we could use surface mining, which is just removing top layers of soils to get at coal beds. Or we might need to use subsurface mining, where we actually dig shafts deep down into the earth to reach coal beds. For oil, typically we drill wells. The wells could be on land, they could be in the ocean. So an oil rig is kind of like a floating boat oil well, if you will. And so the oil well will have a large pipe that goes all the way down to that pocket of oil. So it'd have to drill through that impervious rock layer, pass through the natural gas layer to get to the pocket of oil. Natural gas is similar to oil in the sense of drilling a well. However, it uses a slightly different type of well. So if you have like a clear pocket of gas that is sitting on top of the oil, you could use a traditional similar oil well. I guess you'd call it a natural gas well. But oftentimes natural gas could be found in pockets of shale rock. So again, if it's in a kind of separate layer than the oil, you could easily just tap into that pool of gas and extract it. Oftentimes, natural gas is trapped within these impermeable rock layers, so it's a little bit harder to extract. So we have to use a slightly different well method called fracking. And what it is you inject water, and it has some additives like sand and some chemicals in it that when it gets injected into this pipe that goes vertically into the ground, but then takes a horizontal turn into the shale rock, that water and other chemicals, we often call it fracking fluid, it's going to crack the shale rock that has the natural gas trapped inside of it. The gas will then escape from the cracks and then go up into the well, escaping. We will talk about fracking. There is definitely a lot of environmental considerations when it comes to this process, as there's a lot of environmental issues that come with it. In terms of oil, there is one other way we can extract oil, and it's from something called a tar sand. Sometimes it's referred to as oil sands. So there's this area in Alberta, Canada, that has large pockets of these tar sands. You could find tar sands elsewhere, but this is like the most common location to find them in the world. And what it is sand particles, which what we're looking at in this left diagram here in yellow, the light yellow, are particles of sand. The bluishy gray color is a layer of water that surrounds each sand particle. And then wrapped around all the little sand particles is what we call a bitumen film. Bitumen is kind of a derivative of crude oil. It's one of the components of crude oil. And so what we can do is dig up, literally scoop out of the ground via a mine, that oil sand. So that would be like step one here. The second step would be to take the oil sands and try to separate the bitumen from the sand. So we crush it up, then you're going to extract it. You're going to, again, separate that bitumen, which is a form of crude oil, and separate it from water and sand. You'll dilute it, and that is really just starting the process of refining oil. So it's just another way that we can extract crude oil. When it comes to oil, so once we extract coal, once we extract natural gas, it pretty much can be used to go on and generate electricity. We can burn it right away, generate the heat to make steam, spin the turbine, and so on. When it comes to crude oil, we can do more with it than the other fossil fuels. We can actually take it through a process called fractional distillation, which is really just boiling it at different temperatures. And that allows you to separate the crude oil into different forms that can be used for lots of different things. So at a very, very high boiling point, you can extract out bitumen. So that is what we use in things like asphalt. It's that really dark, viscous, molassesy substance that is part of crude oil. And that is the part that coats those sands in tar sands. This is how we get diesel. This is how we get jet fuel. This is how we get chemicals that are used in plastic. At a really low boiling point, you can extract out gasoline that is used for cars. So we can take that crude oil and turn it into lots of other usable products, more so than just generating electricity. So typically oil is not used for electricity. It is used for powering transportation, cars, boats, planes, as well as, like I said, plastics, asphalt, lots of other goods. So for each of the fossil fuels, I just want to talk about where in the world we can find it, how much it's being used. So there's 3 different graphs here to look at. So the first large one here is oil reserves in the world as of 2020. And so what we see is a heat map here of the different countries. The darker the colors, the more oil that is left in the world, or that we know that exists. So Venezuela is here in South America. You have Saudi Arabia here in the Middle East. They have some of the highest amounts of oil left, followed by places like Canada, where you have those tar sands, as well as Russia, Turkey, and other parts of the Middle East. And then kind of in the middle range, we have the United States has oil reserves. Think of Texas and Louisiana, as well as China and other parts of Central Asia. And then obviously the places that are lighter in color or don't have data, we don't find oil. So in terms of consumption, so countries that are using oil, this heat map comes from 2023 data. So the United States and China are the world's leaders in consumption of oil, followed by Russia and India. In terms of carbon dioxide emissions from the burning of fossil fuels, burning of oil specifically, the United States emits the most carbon emissions from our oil because we are one of the heaviest users, followed by China. The European Union as a whole is in 3rd place. They were higher than China at one point, but have since done a lot of sustainable initiatives to help bring down those emissions. So they've drastically dropped here. So we know that when we burn any of these fossil fuels, the process of burning produces carbon dioxide as a byproduct. Oops. Similarly for coal, as of 2020, most of the coal can be found in the United States, followed by Russia, China, India, and Australia, with a little bit found in Brazil as well as Canada. So that's why the United States, our number one source of electricity, is from coal. In terms of consumption, China does use the most coal. Think about, they have a very large population, and coal is typically the cheapest of the fossil fuels. So it's an easy resource for them to use. They have a lot of it there, so they use it the most. In terms of carbon dioxide emissions, because China has the highest consumption, they also have the highest carbon dioxide emissions associated with coal, followed by India and then the United States. For natural gas, most of the natural gas in the world can be found in Russia, and as well as parts of the Middle East. The United States and China are up there as well, and so is Venezuela. Because if you think back to the formation of fossil fuels, it's very similar with the formation of oil, which is why the reserves tend to be found in similar locations. In terms of consumption, the United States has the highest consumption of natural gas, followed by Russia and China. And in terms of carbon dioxide emissions, the United States is a leading consumer, so we have the leading amount of carbon dioxide emissions, followed by Russia and then all of the European Union. If you notice that most of Africa, there's a lack of data. So it's not that for natural gas, coal, and oil, there is none in Africa. It's just these are regions of the world that have really yet to be fully explored. So moving on to our final renewable energy source, which is nuclear. So the way nuclear energy works, it's similar but yet different than our fossil fuels. So in order to generate electricity, we're going to use a process called nuclear fission. And this is where you take a radioactive fuel like uranium, and we use an unstable form of uranium called uranium-235. And what we do is we shoot neutrons at it. A neutron is a subatomic particle that is inside the nucleus of a single atom. So we take these little teeny tiny particles and fire them at the uranium. And what that does is it causes the uranium to split into smaller elements. And that process releases a large amount of heat. So just as we saw with our fossil fuels that get burned, in this case, the heat is not coming from burning, it's coming from splitting atoms. The heat then is used to make steam. Steam spins a turbine. Turbine powers a generator, which generates electricity. The process here, compared to our fossil fuels, is a much cleaner option for producing electricity because there's no air pollution associated with a nuclear power plant like there is with our fossil fuels. So our fossil fuels emit a lot of carbon dioxide as well as other harmful air pollutants. With our nuclear energy here, it's clean. The only byproduct that we're producing is heat and steam. Now, there is radioactive waste that we do need to deal with. So the actual uranium elements that have been broken down, that needs to be sealed in cases and stored. It is considered hazardous because of its radioactivity, which we'll talk about why that's harmful in just a second. So that is kind of a con of using nuclear energy. The other issue is some of that heat can be considered thermal pollution because what happens is even though the hot water is cooled before it's released into the environment, it still is typically hotter than the environment's being released into. So nuclear power plants will often sit next to an ocean or some sort of body of water, and the hot water will be released into that body of water. And that has the ability to affect the plants and animals that live in that body of water, especially if they have a very specific temperature range that they can survive in. So these are a few kind of downsides to using nuclear. So in terms of that hazardous waste, so radioactivity is really just saying we're looking at the radiation, a form of energy that's given off from the nucleus of an atom as it is breaking down. And that energy, if it's at high enough levels, is harmful to the human body as well as to plants and animals. So at really low doses, you're probably fine. So think of things like getting an X-ray, a CAT scan. You are being exposed to radiation to get that imagery, but it's at low enough doses, it's not going to do anything. If you start experiencing higher levels of radiation, like from the Fukushima disaster that happened in 2011 in Japan, or if you're reaching severe high levels like in Chernobyl, this is where your cells are literally being destroyed. The DNA is being broken up by that radiation. And so you're going to experience vomiting, internal bleeding. And if at high enough levels, you could experience death very rapidly. That's because the radioactivity is literally destroying your cells at the DNA level. So low doses of radiation is not awful, but at extremely, extremely high doses, it is very deadly. So it's important to make sure that any radioactive waste that is emitting radiation is kept away from humans, plants, animals, to make sure that it is not interfering with their cells and destroying them. And so what's important for us to analyze about our radioactive waste is the half-life of the elements, the radioactive substances that are coming out of a nuclear power plant. So a half-life is the amount of time it takes for 50% of that radioactive substance to decay, which means to break down. So for example, it is known that the half-life of cobalt-60, it's a type of radioactive substance, it's about 5.227 years. What that means is in 5.27 years, if you had this cobalt-60 sample, half of it would be gone. Or sorry, not half of it. Half of its radiation would be gone. So if we think of nuclear disasters that have happened, it's important to understand the half-life of the substances involved, because that is going to be able to tell us, when it's safe to re-enter some of these areas. So for example, Chernobyl in modern day Ukraine was probably the worst nuclear disaster in history. And this explosion of the nuclear power plant happened because of a test that failed, and several people died from the explosion, but also the widespread radiation that was released. So that happened in 1986. We are just starting to allow people back into that area for short amount of time because we know based on the half-life, it's becoming slightly safer. But it's going to take years and years and years to actually be able to go back into that area without any radiation concerns. 3 Mile Island was a disaster that happened in the United States, in Pennsylvania. It wasn't a full meltdown like Chernobyl, but there was a testing error. There was no recorded deaths or cancer cases associated with it, so it's definitely not as bad as the other two. Fukushima was from the earthquake and tsunami that happened in 2011 in Japan, and the tsunami basically wiped out and led to the explosion of the reactor core, and lots of radiation was released into the environment. So it's important to become familiar with these 3 examples, especially for the AP exam, because they are, the most well-known examples of nuclear meltdowns. Now, if I were to take our non-renewables and compare them, now these graphs are also going to include renewables on here, but in terms of deaths related to the electricity production of our fossil fuels as well as nuclear, coal, and there's 2 different types of coal on here, and I'm not actually sure of what the difference is, but coal by far and away has the highest death rate associated with it, followed by oil, and then nuclear is way, way, way down here. So people often are scared of nuclear because of those nuclear disasters, but the death rate is drastically lower compared to our other fossil fuels. If we look at a comparison of the safest and cleanest of our energy sources, so again, this is just looking at death rates from specific accidents and air pollution. Nuclear is way down here. Coal is significantly higher than all the others. And if we also associate this with greenhouse gas emissions, so in terms of how bad it is for the environment, coal is still number 1. It's 160 times higher than nuclear. Nuclear energy is way down here in terms of greenhouse gas emissions. Again, it's pretty negligible. So overall, people tend to be afraid of nuclear energy, again, because of those disasters, but it is one of the more safer and cleaner energy sources for our environment.